This video is created as a supporting video of ITU book chapter 9, including real flight test of Parrot Mambo quadrotor drone and simulation results of classic flight. The main literature used on this research are listed as follows: planar formations considering real platforms by Kumar et al., optimal geometries for formations elaborating UAV collision avoidance, better surveillance and mapping by Tomlin et al., analysis of 2D and 3D formation topologies elaborating various formation topologies such as leader, follower, centralized, etc. by Anderson et al., aerodynamics and control of autonomous quadrotor helicopters in aggressive maneuvering, elaborating quadrotor control structure for aggressive maneuvers by Huang et al. The form of quadrotor formation is as follows. The group of quadrotors are flying while preserving their rigid form. A set of homogeneous 5-point agents are taken. The Ch9 cancellation constant epsilon k is obtained as 0.01. The distance constraint dij is obtained as 1 meter. The required vehicle speed is vi bar obtained as 1 meter per second. I run the simulation for checking effectiveness of high-level coordination control scheme ignoring UAV dynamics. P1 is indicating leader's position, P2 first follower's position, P3 second follower's position, Pn and ordinary follower's position. The interagent distances always keeping 1 meter in the steady state and never go under 0.7 meters at transient response. So we are able to keep the rigidity of the initial form of the point agents. So we satisfy the requirements of rigidity and constraint consistency for 5 agents, including 9 interagent distances can be seen easily on the right hand side figures. Path phase of UAV agents in the formation in 3-dimensional space, each color representing different UAV agents. The online flying simulation of 5 agents in leader-follower topology while moving from their initial location to their final destination. Same formation flight for 5 quadrotor agents, we still keep the interagent distance constraints and preserve rigidity and constraint consistency of the formation flight as it can be seen in the figures in detail. 3D path phase of autonomous quadrotor vehicles in formation, each color representing different quadrotor vehicle.
Now we are testing this manual takeoff and then waypoint action in order to see the better reaction of your nested control system. Generally in these systems there are different approaches. One of them is explained as successive loop approach, generally used the control designed for flying vehicles. Now for multi-rotor drones there are nested loops, that means inner and outer loop. Outer loop is taken the position request, the requirements, and then convert to the angular requirements because these systems are work with these angular requirements, angular inputs, and then these angular inputs converted to torques of yaw, roll, and pitch, and then thrust action. Now we will test this flight, which is with research assistant Rahman. Now our is taken care of, and then going back and forth with the controlling sight. Yes. Thank you very much. This is very good.
The distributed coercive motion control system is tested for autonomous agent kinematics moving in 3 axes. The target of the design system, a group of quadrotor vehicles, protects its initial formation shape as it moves from start to finish position. The real flight of Parrot Mambo drone have been tested by many flight scenarios. The performance of the cooperative controllers have been verified by various simulations as the conclusion of this research.